In our first lesson, we discussed propositions, and shortly thereafter we discussed the liar's paradox. That is, the statement that reads, "This statement is false." And what we saw is that this is not a proposition, because if we were to assume that it were true, then the statement itself must be false, and now we have a statement that is both true and false, therefore not a proposition. And similarly, if we were to assume that it were false, then the statement must be true. And once again, we have a statement that is both true and false, therefore not a proposition. Today, we are going to use a similar argument to answer the question that I posed during the last lesson. That is, given any collection of objects, do we have a set that contains set elements? As of right now, it seems that that should be true, because with a set, the way that we define it is a set is just a collection of elements. So if we get a collection of elements, we have a set. But using the argument for the liar's paradox, we are going to go ahead and see that that is not the case. There are things that we can construct that are not sets. So the story begins with George Cantor in 1874. In this course, we're going to be investigating Cantor's set theory. We have already introduced sets. Today we're going to go and talk more about operations on sets. But one thing that Cantor's work did was revolutionize mathematics in the sense that now mathematicians could formally axiomatize all of math. And that was what was happening towards the end of the 1800s and early 1900s. Mathematicians worked at axiomatizing every branch of mathematics, and that is the way that these topics are taught today. It's building on the foundations of sets. And so while sets and their properties were implicitly used at times by mathematicians prior to Cantor, it was not until Cantor that all of this was laid out explicitly along with their properties. But it turned out that things were not as intuitive as they may seem at first glance. And so, as an example, following Cantor's work, we go to arithmetic. That was one of the first branches that was axiomatized. But it was not an immediate thing. Gottlob Frege published in 1884 his Foundations of Arithmetic, which he had been working at that time for several years. And this work sought to axiomatize arithmetic so that we can answer mathematically what is a number. How does one go ahead and prove that 1 plus 1 is equal to 2? How do we go through these topics without going about saying these things are obvious or immediate? How can we rigorously show these ideas? And that was what Frege sought to do. And this work had some flaws, and he continued to work on this and build upon it for the next 20 years. In the early 1900s, he began to compile the work that he had done for the past 20 years to publish a second edition of the Foundations of Arithmetic, which patched some of the logical flaws that had been raised and that he had noticed from his original publication in 1884. However, all of this work was based on axioms, one of which pertains to the question from last time. Given any collection of elements, there is a set that contains them, and that was one of his foundational assumptions. And the thing about foundational assumptions, axioms, is if one ends up being false, the whole system collapses. And that's exactly what happened with Frege's work. And the way that this came about was in June 16, 1902, when Bertrand Russell wrote a letter to Frege. At that time, Russell had been studying Frege's work and had been working on his own Foundations of Arithmetic, what would later become Principia Mathematica, which he published alongside Alfred Whitehead. And so here's the full letter, but I'm going to specifically focus on the following line, and I'll explain what these ideas mean, since it's in a different language than what we have been discussing so far. And so specifically, I want to draw your attention to the following. So he mentions that there is just one point where I have encountered a difficulty, And this is a reference to Frege's work. And so he says, you state that a function, 2, can act as the indeterminate element, and this I formerly believed. But now, this view seems doubtful to me because of the following contradiction. And here's where we get to the famous Russell's paradox. And here, he's using the word W first. Here we want to interpret W to be a set. And so W is the set. So that's how we want to interpret predicate. So with that, this line over here can be interpreted as the set of all sets that do not contain themselves. And Russell writes that from each answer, its opposite follows. And we're going to investigate this in just a moment, because this essentially is the same argument that we just used earlier for the liar's paradox. And in Logicomics, which it takes creative freedom, Russell's paradox was a response to Frege's foundations of arithmetic. One thing that Logicomics does wonderfully is that it incorporates these aspects that happen in the historical timeline of foundations of mathematics in the early 1900s, but it puts Russell at the center of them. In the case of Russell's paradox, he did develop it, but it puts it in a different context. So here we have this scene where he is at a restaurant having a conversation. And so let's run through this and get to Russell's paradox. So it starts off, for example, a set can contain other sets or even itself. How can it contain itself? The set of all ideas is an idea, and therefore it contains itself as an element. And so now here we have a notion where we are viewing sets in a different way. Now we're looking at the set of all ideas. That being an idea itself, now we have a set that contains itself. But of course, not all sets contain themselves. If we were to take the set of all birds, that is not a bird. And so now we have that. And so this leads Russell to the following realization. The set of sets which contain themselves and the set of sets which don't. So what happens? So let's write this down. So let us consider R. So here we have it. We have R is the set of where now we have S, such that S is a set. And S does not contain itself. So S is not an element of itself. And so what I want you to do now is to investigate the following two possibilities. So try what will be the conclusion if we have that R is an element of itself. And similarly, what would happen if R is not an element of itself? And so this is now the liar's paradox once again in the way that we are going to argue it, but now in the notion of sets. So pause the video and give this a try. Okay, so let's go ahead. I'm going to go ahead and work this out. So let's first consider R is in R. So if R is in the set R, then by definition, this is the collection of sets such that S is not an element of itself. So if R is in R, then we have that R does not contain itself, which contradicts the assumption that R is in R. And we now have a problem. So we have a contradiction. We have that both R is an element of itself and it is not. And so that is our contradiction. But if we do the same argument, where now we take R is not in R, then to not be in here, that would mean that R must contain itself, since that is the defining property of how sets are in R. So if we have a set that is not in here, it must be the case that it must contain itself. And so now we have that R is an element of itself, which is again a contradiction. So therefore, R is not a set. And now we have now our first example of something that is not a set, even though we have a collection of objects, elements, namely those sets that do not contain themselves. And this was a big problem, as I mentioned, because Frege, as what he called his Rule 5, assumed that given any collection of objects, there must be a set that contains them. And this led to the whole collapse of Frege's program. Frege did respond to Russell, and this is a portion of Frege's response to Russell's letter. And so he writes, "Your discovery of the contradiction caused me the greatest surprise, and I would almost say consternation, since it has shaken the basis on which I intended to build arithmetic. It seems, then, that transforming the generalization of inequality into an equality of courses of values is not always permitted, that my Rule 5, the one we were just discussing, is false, and that my explanation in section 31 are not sufficient to ensure that my combinations of signs have a meaning in all cases. I must reflect further on the matter. It is all the more serious since with the loss of my Rule 5, not only the foundations of my arithmetic, but also the sole possible foundations of arithmetic seem to vanish. Yet I should think it must be possible to set up conditions for the transformation of the generalization of inequality into an equality of courses of value, such that the essentials of my proof remain intact. In any case, your discovery is very remarkable, and will perhaps result in a great advance in logic, unwelcome as it may seem at first glance." And Frege, in the time that followed, tried to patch up his Rule 5, making restrictions so that he can still allow his work to succeed, but he was not successful in doing so. Eventually, Frege's work was overshadowed by the publication of the Principia Mathematica, which we mentioned in the first lesson, where Russell and Whitehead proved 1 plus 1 is equal to 2 in 362 pages. But that work, the reason for its length is that they were able to bypass Frege's Rule 5, but that led to complications, because in order to bypass it, it led to more to stricter axioms to work with, and therefore the argument to get to 1 plus 1 is equal to 2 was a much more complicated path. However, today it is not the axioms of Principia Mathematica that we base arithmetic on. While it is valid, there's a simpler axiomatic system that was actually published around the same exact time as Principia Mathematica, namely what are known today as the Zermelo-Franco axioms. And so these are the ones that all of modern mathematics is essentially built upon. And with these, one can then define what it means to be a number. How does one add numbers? These are topics that we will not be discussing as part of our course, since this is a second course in set theory. But if you are interested, I highly recommend Paul Hommel's naive set theory, which goes into the Zermelo-Franco axioms with the goal of constructing the natural numbers, the integers, and then building everything up, set theoretically. Whereas the goal for this course is to use set theory, but specifically with the goal of getting the foundations of how one proves statements in mathematics. And so this is a much deeper investigation in terms of the foundational aspects. And so I highly recommend Paul Hommel's naive set theory if you want to pursue this. And so this is the cover of the book. Now, Frege was absolutely right in his conclusion of his letter that Russell's discovery will perhaps result in a great advance in logic, unwelcome as it may seem at first. One of the things that mathematicians were hoping to achieve in making mathematics axiomatic was the following. Given any question in math, can we prove or disprove the statement? And building on Russell's and Whitehead's work, Kurt Gödel in 1933 gave an answer that flew in the face of what mathematicians had hoped. Namely, he showed that any axiomatic system from which arithmetic can be deduced will have undecidable statements. That is, there are questions that we will never be able to prove or disprove. And so this is one of these questions we will actually be seeing later in our course, which is known as the continuum hypothesis. So we'll come back to Gödel and how this statement plays a role in what we will be investigating in our course. So now let us return to sets themselves and define operations on sets. So namely, if we have two sets A and B, we can define their intersection, their union, and their difference. And so the intersection of two sets A and B is defined as those elements X such that X is in A and X is in B. The union is defined as those X's such that X is in A or X is in B. And finally, the difference, which is A slash B. Also, this is another notation that is perfectly valid, A minus B. And so depending on which book you're using, these are the two notations that are used for difference. We can also use them interchangeably. And so with a difference, we have that X is in A and X is not in B. A way that we can go about visualizing each of these is via Venn diagrams. And so for example, we can go ahead and consider our set A as if it was this ellipse and our set B to be this other ellipse. And so here's our A, here's our B. And then when we're looking at the intersection, we want all the elements that are both in A and B. So that means everything in between the two. And so we're looking at this portion right here. And so this here will be our A intersect B. Similarly, when we look at the union, we can have another, we'll draw another Venn diagram. And now with a union, we are looking at everything in A and B. And so consequently, in this case, we have that the set A union B is the whole thing. And so now we're looking at everything. And so here we have A union B. And finally, with the difference, we go ahead, draw another Venn diagram. And now we have A minus B. So we're looking at everything in A, but we have to remove everything in B. So we're eliminating B from this. And so we're only going to have the left portion here. And so now this here would be our A minus B. And so now, with Venn diagrams, this raises the question, can we use Venn diagrams to prove equalities of sets? So for example, what if we had the following? So we want to show that A intersect parentheses B union C is equal to A intersect B in parentheses, then union parentheses A intersect C. So can we use Venn diagrams to show this? And the answer is no, but Venn diagrams do provide good intuition for deducing whether the statement that we want to show is true or false. So in this case, this is a true statement, but if we wanted to show its validity via Venn diagrams, we can use that to enlighten our path to know if the argument that we want to show if it's right or not. So let's go ahead and do Venn diagrams, and then we're going to discuss how to rigorously show this. So I'm going to go ahead and draw a Venn diagram with 3 circles for A, B, and C respectively. So here we have our Venn diagrams. I've done 2. So on the left, we are going to investigate A intersect parentheses B union C. And on the right, we are going to investigate A intersect B union A intersect C. And see that both of these are equal by looking at the Venn diagrams. But again, this is not a rigorous proof, but we will show how to do that with what is known as an element chase argument. And so here, we're looking at, let's look at what B union C. So with B union C, we're looking at the union of both of these circles. But then we want to intersect that with what? With A. And so we're looking at the union of the circles for B and C, but we only want the portion that is in A. And so now we're looking at this portion right here. And so that's what we will have. And so here we have it. We have that this is the portion of B union C that intersects A. Now if we go and turn our attention to A intersect B union A intersect C, we can see that A intersect B is going to be this portion right here. So this here will be the A intersect B. And so let's go ahead, shade that in. And similarly, if we look at A intersect C, what we are going to have is that that is going to be this portion right here. And so that will be the intersection of A intersect C. And so now we're going to have, change the color. And so we do have this overlap now. So I lost my screen there for a moment, I apologize. But now we have with A intersect B, we're looking at this here. And A intersect C, we're looking at this portion right here. And so the union will be the whole collection. And so by Venn diagrams, we see that we do have equality. Now, how do we show this rigorously? Well, let us first talk about subsets. And so if we have two sets, A and B, we will say that A is a subset of B if every element of A is also an element of B. And we're going to be writing this symbol to denote that A is a subset of B. And we are going to say that A and B are disjoint if they have no common elements. And so, in other words, if two sets are disjoint, that means that when we take the intersection of A and B, then we get back the empty set. And now, let us revisit what we mean by when we say two sets are equal. So two sets are equal if they have precisely the same elements. But now we can write this symbolically in the following way. So two sets, A and B, are equal is equivalent to the following. For each x in A, so for each element x in A, we have that x is an element of B. But notice that this is what we mean to be a subset. And so that's one part. So we have here A is a subset of B, is what we're writing here. And for each x in B, it is the case that x is in A. And that's now what we mean by a subset. B is a subset of A. So therefore, two sets are equal is equivalent to A is a subset of B and B is a subset of A. And in a bit, we're going to come back to this and rewrite these in terms of biconditional statements. And so now we have this notion of subsets. And with this, we can now come back to our statement about A intersect B union C equals A intersect B union A is intersect C. So what we're about to do now is an example of what is known as an element chase proof. So we are going to prove this. So an element chase proof. And so what this means is that we are going to choose an element in here and then show that that element is also in here. And so let's go ahead and do this. So proof. We're going to go ahead and let X be in A intersect B union C. Well, what does this mean? We have our definition of intersection. That means that that's the collection of x's such that X is in A and X is in B union C. So this is equivalent to X is in A, and the intersection will be read as an and, X is in B union C. So we got this here. But now we can do the same thing. We have the definition of what it means to be a union. And so now this means that X is in B or X is in C. And so now this also is equivalent. So this is equivalent to X is in A and X, and I'm doing something wrong, and I'm going to explain why this is wrong in a moment. So I just went ahead and replaced the definition for what it means to be B union C, but I made a fatal error. When I do this, now there's ambiguity. We have an and we have an or. But which goes first? We know that these are not associative. And so we need the parentheses. This is important. So that's one thing just to be careful when writing these things down. So we have X is in A and X is in B or X is in C. Now observe that what we have is essentially a statement of the form P and parentheses Q or R. And we have seen that this is equivalent by the distributive property to be P and Q parentheses or P and R. And so now what we end up getting is that this statement here is equivalent to the following. So by the distributive law, and I'm going to go ahead, and this is a reference to this statement. To X is in A, and I'm going to put parentheses, and X is in B, or X is in A, or X, and X is in C. But now this is equivalent to the following. So now we're going to do it in reverse. So this is equivalent to, by reversing the definition, so X in A and X in B, that is the definition of what it means to be in the intersection. So this is the same as X is in A intersect B, or X is in A intersect C, which is equivalent to X is in, so now we use the or, and we reread that as union. And so this is the same as saying X is in A intersect B, and now the or takes the place of the union, and A intersects C. But because of the equivalences, what we have done is show that to be in here is the same as being in here, which is the same as being in here, which is the same as being in here. And now the whole process reverses because of the equivalence. So we choose an element in here, and we can work our way backwards. And so that's the benefit of all these equivalences. And so we have now, so therefore, we do get the equality. And now we're done. And so to finish the proof, I'm going to write this tombstone. So this is this symbol here, and I just write this as a comment. This is known as the tombstone, which signifies the end of a proof. We can also write QED. And now QED is Latin for quod erat demonstratum. And now this, what this means is what was to be shown. And so this is what signifies the conclusion of a proof. And so when we write a proof in math, what we will do to finish it off is either write the tombstone or write out QED to indicate to the reader that the proof has now been concluded. So let us do another example. So here's the theorem 1.4.7 from our book. So for any sets A and B, we have that A union B minus B is a subset of A. Now, while Venn diagrams do not constitute a proof, they do give us some visualization of what is happening. So this is optional, but let's go ahead and draw a Venn diagram to see what is A union B minus B. And so here's our Venn diagram. And so we can see that if we take A union B, what we are doing is taking the whole union of the two quantities, the A and B. But then if we take away B, if we take the difference, that's all the elements in the union of A union B, so everything. But then we want to remove B from here. And so what that gives us is this here. And so we can see now that, yes, this is in fact a subset of A by the Venn diagram. But now to show this rigorously, we want to go ahead and do another element chase. And so proof. So we're going to go ahead and let X be in A union B minus B. Now we apply the definitions. So now this, by definition, is equivalent to X is in A union B and X is not in B. And so now what we have is that the A union B breaks down even further, as we saw just now. So now this is equivalent to X is in A or X is in B and X is not in B. But I made another error here in that we need to be sure to put in those parentheses. And so we have X is in A or X is in B, and that's in parentheses, and X is not in B. But now what we have is a statement of the following form. We have P or Q and not Q. But this here, once again, by the distributive property, this is logically equivalent to P and not Q, or Q and not Q. But now this is a contradiction. And by the contradiction law, because now we have an or statement, we have that this only relies on P and not Q. And so this here is logically equivalent to, by the contradiction law, and so over here, I did not write this down, but this was the distributive law, to P and not Q. So now, what we have is that this statement here, so in particular, star is equivalent to X is in A and X is not in B. But specifically, we do have that X is in A. Hence, X is in A, which shows that A union B minus B is a subset of A. And we're done. So we have our proof, but is it a good one? Of course, that is a subjective question. But in mathematics, when we say a good proof, we are saying one that can be understood by someone with a requisite background. And nothing is left to the reader. That they are able to start and go through the end and understand every step along the way. And let's go ahead and now analyze what I have in front of us. Up to here, everything has been defined, but then I introduced this P or Q and not Q and made a reference to how we deduce this using propositions and logical connectives and the laws from the last lesson. But I never said what P, Q were. It was understood as I was explaining it out loud that P is X in A and Q is X in B. But someone who did not hear the verbal explanation is then left with a gap where we go from here and we are expecting that reader to make this deduction that this is what we have. And so oftentimes when we write down a proof, we don't necessarily know where we are headed. And so you want to interpret your first proof as essentially scratch work. And once you finish the proof, then you want to go ahead and rewrite it in the nicest, most elegant way. But at times that may remove the intuition of how we got there. So what I just described is best elucidated by the following comic strip due to Abstruse Goose. When we're working on a math proof, we don't necessarily know how we can get to our conclusion. Let's call our conclusion B and our starting point A. We may take some turns and those may lead us in the wrong direction and then we have to come back. And so for example, in this comic strip, they're going from point A to B and they don't really get there and they make a bunch of wrong turns, eventually getting to the moon. And then finally, when they get to B, they write down the shortest path from A to B. And that is usually what is the benchmark for a good proof, that the reader should be able to go from A to B, even if it comes at the cost of intuition. And so one thing I want you all to practice as you write down your proofs is to get in the habit of first doing your scratch work. And so that's the proof where you may be taking the wrong turns and then having to return back to one of your assumptions. And then once you finally get to the conclusion that you want, then rewrite it so that it goes in a way that explains to the reader how you go from your starting premise to the conclusion in the most efficient way. And so now that's one thing that I want you to practice as we go on. And so I'm going to come back to this proof in just a moment and rewrite it in a different way, while at the same time explaining each step along the way. But before we do that, let's go ahead and introduce a couple more connectives, namely the conditional and biconditional. And with those, I'm going to come back and rewrite this proof in just a moment. So one connective we have not discussed yet is if-then. And so we are used to seeing in mathematics statements of the form if and then. And so, in other words, we can put over here if P, then Q. Symbolically, we can write this as P implies Q. And so now P here, of course, is the hypothesis, and Q is the conclusion. And so this symbol is an example of what is known as a conditional. This is the name of the connective, in the same way that and we call the conjunction. Here we have conditional. We also have if and only if. So P, if and only if Q, which is defined as P implies Q and Q implies P. We also have this here. We can call this if and only if, or equivalent. And so these are the various terms that we can use to talk about these symbols. Now, these logical connectives also have truth tables, and that's one thing we are going to investigate in just a moment. But first, I'm going to discuss sort of the phrasing, since there's various ways that we can define if P then Q. We also have statements like necessary and sufficient. And so in terms of phrasing, we have the following table. So here's our table. So we have P implies Q is our if P, then Q. We can also say that as P is a sufficient condition for Q, since if we have P, then we get Q. If we were to now have Q implies P, of course this is our if Q then P, but we can also say this in a different way, where now we say P is a necessary condition for Q. And finally, we have our equivalence, P if and only if Q, which we can abbreviate to just IFF. And this is saying that P is now a necessary and sufficient condition for Q. So what are the truth tables for these? In the case of the if and only if, we just really need the implication. We just need the if-then, because we can get the if and only if by its definition. P implies Q, and Q implies P. So if we have the truth table for P implies Q, we can then get the truth table for if and only if. So let us investigate the truth table for if-then. So let us investigate the truth table for the conditional, P implies Q. Now, the first two statements, we know that if P is true and Q is true, then we expect the implication to be true. Now, if Q is false, then Q does not follow from P. So in that case, we are going to get false. Now, here's where we take a departure from how if and then are used in everyday language. Mathematically, when we have a false premise, we are actually going to get that these two truth values are true. To justify why that's the case, let us consider the statement P and Q implies P. This is a deduction that we want to always be true. So we want this to always be true. But now what if we do a truth table for this? Well, if we expect this to always be a true statement, then this is going to be a tautology. And now, let's do a truth table here. So here's our truth table. So we know that P and Q, that is true if P and Q are both true, and otherwise, it's always going to be false. But we want, logically, to get the implication P and Q to imply P to be a tautology. So that's what we have in this here. But now let's analyze. The P and Q, that's the hypothesis. And so P and Q is taking the role of P here. And so if we want this to be a tautology, now that this condition is going to force these two to be true. Because what we have is that if the hypothesis is false, and so that means these three possibilities here, and so we take the hypothesis to be false, and the conclusion, which in this case is P, to be true, then we have the instance false and true. And so we get back the value true in this case. And so that's going to force this here to be true. And similarly, in the case when P and Q is false and P is false, we are also forced to have that this is true. And so we have our truth table. As a consequence, we have the following. From a false premise, we can deduce anything. To illustrate this, there is a story that Bertrand Russell was once giving a lecture on logic, and a student raised their hand and asked, in that case, given that 1 is equal to 0, prove that you are the Pope. To which Russell gave the following argument. And so here's the statement. So we want to show that from 1 is equal to 0, you can get that Russell, or you, or any of us, is the Pope. And so here's Russell's argument. If we go ahead and add 1 to both sides, gives that 2 is equal to 1. The set consisting of Russell and the Pope has 2 elements. Therefore, Russell is the Pope. Since 2 is equal to 1. And so then it has 1 element, and so Russell and the Pope must be the same individual. And we now have that from 1 is equal to 0, we can deduce that Russell is the Pope. And so this is a way of seeing how we can get from a false premise to any statement. And so that's how we think about implication in logic and mathematics. So now let's go ahead and do the biconditional. So the if and only if. So for the if and only if, we want to have a couple more statements here. So let me just go ahead and rearrange this. So to do if and only if, the biconditional, we need to fill in the table for Q implies P. And so what we are going to have there is just here Q is, in this case, is going to be true. Now for the second line, Q is false, and so this is going to be true. And similarly, in the third line, we have Q is true and P is false, so this is going to be false. And finally, we have false, false, so this is still going to be true. And from this, now we have the AND statement, so we need both of these to be true simultaneously. So we get true, in this case, false, false, and true. But now notice what this is matching up with. We get true if P and Q are both true. If P is true and Q is false, we have false. P is false, Q is true, we have false. And finally, if both P and Q are false, we get back true. And so in other words, the truth value for P and Q are exactly the same when we have truth values here, and hence the word equivalence for the if and only if. In our next lesson, we are going to continue investigating conditionals and biconditionals. But to finish it off for today, let us rewrite the proof from earlier. So I've gone ahead and included the proof that we did earlier. And so I'm calling this now scratch work, because this is not a good proof, as I explained earlier, in the sense that whoever reads this proof, we are tasking them with having to interpret what the P and the Q are, since they were not defined in the proof. Yes, they were said verbally, but the goal of a proof is that it should be read standalone, that whoever is reading it could follow each of the steps without tasking them to do additional work. And that's what's happening here. Whoever reads this is being tasked with making the observation that this P is X and A, this Q is X and B, and then seeing how this connects to what we have below to get our conclusion. So let's go ahead and redo the proof, and this is an example of what is known as a two-column proof. And so I'm going to go ahead and write, observe that if we choose X in A union B minus B, that this here is equivalent, so now I'm using the biconditional for equivalent, to X in A union B, and X is not in B. And usually with a two-column proof, we explain the definition, the reason for why this holds, and so this here is by definition. And now we have that this is also equivalent to X in A, and then parentheses, of course, or X in B, and X not in B. And once again, this is just the definition of what it means to have a union. And so there's technically, to be precise, definition of union, definition of set difference. And from here is where we went and made the jump using the distributive law. But now I'm going to go ahead and write the distributive law from here and then explain it on the right hand side that we're using the distributive law. And so here we have X in A and X not in B, and or X in B and X not in B. And this is by the distributive law. And now this is equivalent by the contradiction law, to X in A and X not in B by contradiction law, which then implies that X is an A. This is a true statement. Or, if we prefer, we can just finish it off here and then say, consequently, X is an A, which shows that we have the desired inclusion. Since we chose an element in A union B minus B, and now we have shown that that element is itself in A, and so by definition we have that this is a subset of A, which is what we wanted to prove. And so we are done. And so now the benefit of the way that we wrote this down is that along each step of the way, we are explaining to the reader what is being used. And so this here is an example of a proof, as I mentioned, a two-column proof in the sense that we have our two columns, we have what we started here, and on the right hand side we have all these equivalences that we're tagging along and explaining why those equivalences hold. And so this is one example of a proof where in this course we're going to see various different ways and arguments. And so in this case this was nice since it was an element chase. An element chase in the sense that we chose an element here and then chased it around to get that element was also in A.